In this video, we're going to talk about Venn diagrams, which are a useful way of visualizing general sets. So for example, if we want to visualize the set A union B for just any set A, any set B, we can draw two circles that have some intersection. And the points in A union B would be described by everything that's in A or B or both. So that's how we could just visualize A union B. If we wanted to visualize A complement, that's everything outside of A. So we now need a universal set indicated by that square around the set A, that rectangle around the set A. And we want to include all points or all elements that are outside of the set A. And so this is how we would denote A complement using a Venn diagram. So I'd like you to sketch the following sets: A intersected with B, B minus A complement union B complement, and A union B complement. Pause and try those out. Okay, A intersect B, that is everything that is in sets A and B, in both A as well as in B, the intersection. So that's how our drawing would look. B minus A, the difference of those two sets, that's all elements that are in B and not in A. So that would be the visualization as a Venn diagram. A complement union B complement. If we wish, we could draw that in steps. So if we look at A complement, let's use a new color. A complement, that would be everything outside of A. So everything outside of A looks like this. And then B complement, that's everything outside of B. And so then when we think about the union of those two sets, when we union those sets together, we see that we get everything except what's in the intersection of A and B. So in other words, A complement union B complement is given by everything that is in B complement as well as everything that is in A complement. So that would include this. And so this is A complement union B complement, everything outside of this region right here. All right, how about A union B complement? So again, we could draw that in steps. We could first draw A union B. So A union B, as we saw before, is drawn in this way. And so A union B complement, everything outside of A union B, would be given as this set. So everything outside of A or B or both. We can also draw Venn diagrams with three sets. So for example, if we wanted to draw A intersect B intersect C, that would be all elements that are in A and in B and in C. So those elements that are in the intersection of those three sets. With that in mind, I'd like you to try drawing A union B intersected with C, as well as A union B intersected with C, and then also with parentheses in different places, A intersect B intersected with C, and A intersected with B intersect C. So pause and try those out. Okay, so A union B then intersected with C, we can again draw in steps if we wish. If you do this with your homework, just make sure that you clearly label your steps. So A union B, everything in A or in B or in both. So all of these points, all of these regions are places where the elements would be in A or in B. Then if we want to intersect that region with C, that would only be this region right here. So that's A union B, then intersected with C. Just like if you're evaluating algebraic expressions, if you see parentheses, you want to do the thing in parentheses first. Okay, how about A union B intersected with C? So first we'll do B intersected with C, the piece that's in parentheses. B intersected with C are the points that are in B and in C. Then if we want to union that together with A, we would have everything that was in A as well as the points that are in B intersect C. So we also have this region as well. Something to note here is that these two sets are not equal. So we see that these two sets, A union B in parentheses intersected with C, is not the same set as A union B intersected C with C in parentheses. So the parentheses do matter when we have a mix of unions and intersections. All right, how about A intersected with B, then intersected with C? So then we're just looking at the things in A and B together and also in C. That is going to give us the things in A intersect B. We know where that is. Also intersected with C is just this. If we look at A intersected with B intersect C, so if we're looking at this region first and then intersecting it with A, again, we just get this region right here. So these two sets are equal. So if the symbol stays the same, if we just have if we just have intersections, and also this would also be true if we just had unions, then we say that this is associative because the parentheses does not matter. A intersect B intersected with C is the same as A intersected with B intersected with C, and it's also going to be the same as just A intersect B intersect C without parentheses, which, as we saw above, was not the case when we have a mix of unions and intersections. Next, I'd like you to draw Venn diagrams for the following two circumstances. So first for A intersected with B complement, and then for A complement union B complement. And after you draw these sets, I'd like you to see, does it appear to you that these two sets are equal? And similarly, do the same for A minus B union C and A minus B union C. So grab some paper if you haven't already, pause, draw those sets, and we'll talk about them together. All right, again, I'd recommend sort of doing these in steps. A intersected with B, we have just the intersection of those two sets. A intersected with B complement then is everything outside of that intersection. So everything out here is A intersected with B complement, everything outside that blue set above. Now if we want to draw the union of A complement with B complement, that's everything outside of A, everything outside of A, and then everything outside of B is B complement. And when we draw the union of those two blue sets, we then get everything outside of A intersect B, everything outside of A intersect B. And so we see that this, in fact, when we get the union of those two sets, is the same as the previous set that we had. So this is an illustration that it appears that the complement of A intersect B is equal to the complement of A unioned with the complement of B. That's not exactly a proof. Later in the course, we'll learn to prove statements like this more formally. Okay, how about the other two sets? So first we've got A minus B unioned with C. If we want to draw this in steps again, A minus B, everything that is in A but not in B. And then if I'm unioning that with everything in C, my next step would be taking that set and as well including everything that is in C. So that would give me all of that. There is my set A minus B union C. My second set I'm interested in is A minus B union C. So parentheses are in a different place. I want to start by drawing the parentheses first. So B union C, that would be everything that's in B or C or both. So that's B union C. If I draw A take away B union C, A without B union C just gives me this purple shaded region. So I see that the two sets I was interested in checking on are not equal. So these are not equal as sets. Here's one last example to try. Here I'd like you to actually work backwards. So here we've got a picture of a Venn diagram with regions already shaded, and now I'd like you to write an expression for this using sets. So how would you describe this using sets? And there are different possible answers you could give, but I will pause and let you think about it. Okay, so one possibility, there's more than one possibility, but one would be, we could think of this as A minus B as sort of everything over here, and then we could also union that together with B intersect C. So I could union that together with the set B intersect C. So that's one possible way that you could describe this set. If you're curious about whether the way that you described your set also works, and you're not sure, feel free to send me an email or show up at office hours and ask. All right, so that is it for this video.